Hello, and welcome to lesson 20 of this Introduction to Probability of Wolfram. The topic for this lesson is transformed distributions. Let's begin. Probability distributions can be addressed as random variables. As such, it's theoretically only natural to consider a function of random variables. In practice, transformed distributions are useful for mathematical modeling. You'll learn about nonparametric distributions and how to do the different operations of transform distributions. Let's take a moment to analyze distributions formed by data, since data science is a major application of these concepts. In Lesson 7, some distributions were data-driven, meaning the PDF was not a simple math function, but rather the frequency of each value in a dataset. If you want like that, the simple, close representation of data as a distribution, use empirical distribution. If you want values to be binned over intervals, often useful for real contexts, use the histogram distribution. And if you want the distribution that gives a smooth representation of data, using interpolation, use smooth kernel distribution. Now that popular parametric and nonparametric distributions were covered, I'll assume you're comfortable using any parametric and nonparametric distribution function. Notice functions of random variables aren't completely new to you. If you did the previous lessons, you'll notice we were already calculating expectation on a function of random variables. Here you have the expression of that function of random variables and the distributions of the variables. To prove this is equivalent to what you were doing in expectation, you can take the expectation of x of a transformed distribution and compare it against the expectation of that function over this simple distribution, and the result should always be the same. The transformed distribution function, however, allows you to make a function of random variables a distribution, making the analysis of that new distribution much easier, not just for expectation, but also for any other function, like PDF, probability, or random variate. How can you transform a distribution to fit your need? The first operation is shifting, where adding a constant will shift the domain of a distribution, like with this zipped distribution. To visualize the shift, plot the original distribution together with the shifted form, which, as you can see, was pushed forward. When shifting by a constant k, the mean is also shifted by k. What if you want to change the size of the domain? Well, that's called scaling, and all you need to do is to scale to multiply the variable. When multiplying by a constant k, the standard deviation is multiplied by the absolute value of k. Taking as an example the beta distribution, multiplying by 2 and dividing by 2, you can see that when all three distributions are visualized, the factor multiplies or divides the size of the domain. If you deal with unknown transformations, you may want to simplify formulas using assumption, which simplify computations and algebra. For example, on a normal distribution, the PDF will force the absolute value of a factor. To avoid this, assume the factor is positive, and the PDF won't have to force it. Enough with constant factors. Let's deal with variable transformations. What happens when you sum two random variables? Sums of random variables can be thought of as multiplying their PDFs. For example, take consumer prices of rice and flour in Europe. Since these are basic and linked products, it can be modelized as two distributions added together, which are log distributions in this case. As you can see, the data seems to correspond to the model. Then what happens when you take the product of random variables? Well, there's no easy answer to that question. Random variable products are an active area of research. While computing it is possible, the meaning of that operation is highly dependent on your application. As an example, you can take two distributions, their product, and visualize. Finally, sometimes it may make sense to use nonlinear operations. For two random points on an interval of 0 to 1, the expected distance is always positive. If the points are uniformly distributed, you can take the mean of their absolute value to get the expected distance between them. But how do you go about applying this in practice? Let's say you're trying to modelize a dataset of abalone heights. Your dataset should follow a logistic distribution of beta 0.021. If you compare the guessed distribution and the data, you'll see there's a clear problem in shifting and a bit of scaling. To adjust, you can add to the distribution the mean of data to get a better model. Scale by just a bit, and you'll see when a better model is plotted against the data. So to summarize, transformed distributions are probability distributions based on functions of random variables. Use empirical distribution, histogram distribution, and smooth kernel distribution functions for data distributions. Useful operations for transforming distributions include shifting, scaling, sums, and products. But as you've noticed, there's a major limitation here. These methods don't allow for you to change easily the shape of a distribution. To be able to draw probability distributions more closely, you need our next tool, mixture distributions.